Hi, in the last video we were doing a thermodynamics simulation in Python and we arrived at this point. So we have particles in a box, they are free to bounce around, they can bounce off the sides of the box and they can bounce off each other. I highlighted one of the particles so that we could track it. And it's quite clear from following this red particle is that sometimes it moves with a low speed, sometimes it moves with a high speed, sometimes it moves with a speed in between. It's constantly colliding, bouncing around and changing speed. But this also happens for all of the other particles in the simulation. So let's go ahead and try and visualize that. So this video series is all about trying to visualize these phenomenon, and then we're going to use our visualizations to actually get a deeper understanding of thermodynamics. Let's go ahead and add a bar chart underneath, which will represent the histogram of particle speeds. So to do that, we go to where we're plotting, and we're going to create a bar chart, call it bar, but we need two plots. So rather than have a single axis on our figure, we're going to introduce a second axis called ax2, so it doesn't break any of the code for ax1. And then we're going to set the plot parameters, copy and paste this over. So we're basically saying create a figure that's 5 inches wide by 9 inches high with 2 rows. We're also going to set the aspect ratio to equal on the first plot, so we're going to try and maintain it as a box rather than have it stretched out. And then for the bar chart, what we're going to need is we're going to have to quantize our speeds. So the easiest way we can do that is to say, so Vs can be our speeds. Let's say it's a linear space, so it goes from 0 to, let's say, 2 for now, in 10 steps. So we've created an array that goes from 0 to 2 in 10 steps. And for our bar chart, we're going to be doing x2. That's our second axis on the figure, bar. And then we're going to want to plot, just initially, nothing. We need it so we can access the bars. We're also going to put in some other variables to this bar chart. So we're going to set the width is equal to 0.9 times the spacing. So that means we'll have a little gap between each of the bars. I'm going to align it to the edge, which will be aligned to the edge of these speeds. And we're also going to give it a tiny bit of transparency so that later on we can see a curve behind it. Now we need to do the same setup for axis 2. Did for axis 1, for axis 2, but this time we're not setting up between -1 and 1, or the simulation height. We're setting up between, on the x-axis, between the smallest speed that we're going to quantize and the largest speed. And likewise for the height, for now, what we'll do is we'll just set that between 0 and the number of particles. And we're going to go up here and we're going to create some variables, sim variables. And let's create number of particles, n. Likewise, when we create the sim class, the initializer function accepts an argument np, and we'll call that the number of particles. So we create 10 particles in the box, then we create a bar chart that goes from 0 to 10 and quantizes those particles into 10 different bins, 9 different bins actually. These are the edges of the bins. Yep. Now what we need to do is we need to create a histogram. The easiest way to create a histogram, we want to create this every time during the plot. So we want to do numpy. So we need to create a histogram of all the particle speeds. So the first thing we need there is we need a way to actually be able to extract the particle speeds. We've already got a function that does the particle positions, already got a function that does the particle colors. Let's go ahead, do one that gives the particle speeds. And so it'll be self.particles. We're going to extract the particle from that. We're then going to extract the speed. But remember, speed is this is a vector. We're after the magnitude of that vector. So we can do the square root of that. Also do the dot product between particle speed and itself. This now will return a list of all the particle speeds. And from that list, we'll be able to generate a histogram. Particle speeds with an S. We can do numpy.histogram. Call the function particle.speeds. Yep. Then the histogram function also requires several other things. So it's going to require the bins. If I do this, so bins equals VS, so we know that our bins are is the vector defined by this VS. So maybe these outer edges of the bins. And then what the histogram returns is the frequencies and the bins. Of course, remembering that it's not particle.speed, it's particle.sim.particle speeds. Yep. Again, just keep checking. I've not broken anything yet. So we've created a bar chart with nothing there. You see from this bottom, it goes from 0 to 2 like we defined, and 0 to 10 also like we defined. Now what we need to do in our update function, we need to be able to put those frequencies, so how many particles within each bin, into the bar chart itself. So for that, we can say for the rectangle, the bar chart itself, this bar variable here has a function called dot patches, and that will return the rectangle that's using to represent the bar. Then we can say get that rectangle for the bar, and also the frequencies which we've just calculated from our histogram. Zip those together. So that means it will return every loop of the iteration. It will return the rectangle for that current bar and also the height given from our frequencies. Then we can say rectangle.setHeight equals to that height. Go ahead and run that. And we see it's not working. And that is because what we need to do here in the update function is we need to return bar. So the return value from the initialization and the update function is a list of artists which the plot can redraw, or the plot should be redrawing. So now we're telling it, I've changed the height of the rectangle, so the height of the bars, it needs to be redrawn. Then we come in here and realize that actually bar is not the rectangles themselves, it is the patches. What we need to say is extract the rectangles from the bar object, redraw all of them. Of course, the reason why this isn't working now is because we need to do the same initialization. Both those in, we should see rectangle start to draw. So as the particles start to bounce off each other, you'll start to see something very interesting when they eventually do. Yep, let's go ahead and add some more particles to the box. Let's go ahead and add 20 particles, and then watch what happens. As the particles start to bounce off each other, you see that where all the particles had the same speed initially, speed distribution begins to change. So we start to get a range of speeds. As we see now, the red particle has been very, very slowly. It's quantized in here. Whereas as the particle begins to collide, it can pick up a bit of speed and it'll be redistributed into a higher bin. If we go ahead and change the number of particles to something insane, like 100, so this might run very slowly, but what you'll see is that as the particles bounce off each other and you have a large number of particles, this histogram starts to become a lot smoother. It starts to jiggle about less relative than when we have a small number of particles. So we see here there are some particles moving very, very slowly. So these have undergone a collision, gives them virtually no speed, so they get quantized down here. Likewise, they have the odd particle moving very, very fast, get quantized here. But on average, as you see, the particle speed is somewhere in the middle. But it doesn't mean, so even though there's an average particle speed, it doesn't mean all the particles are moving at that speed, and that's very important. That's a very profound consequence of the thermodynamic and the Maxwell-Boltzmann distribution, is that just by considering solid spheres, solid particles in a box that can collide elastically from each other and from the edges of the wall, so no energy is escaping, is that you end up with a distribution of speeds. This is very interesting. So this is where the sort of the deeper understanding of thermodynamics starts to come from. So this is really nice. Really, really nice simulation for this. Let's go ahead and just add some nice to haves so we can start making our plots a little nicer. The first thing we want to do, I'm going to remove these tick marks. It doesn't really make sense. We don't really need to see the x and y coordinates of the box, and also we'd like a label on these two axes on the bar chart. So we can go ahead and say, let's set the labels on the bottom plot. So we can have particle speed in meters per second, and then the number of particles on the y. And then we can go ahead and remove the ticks. The other upper particle box, we have that there. So the x ticks equal to an empty list, y ticks equal to an empty list. Go ahead, and there we are. Again, something that looks a bit more easy on the eye. Starts to reveal some of the nice physics. Now, I'm not a big fan of how jumpy this is, so how much this jumps around. What I would like is sort of average. So rather than just showing the instantaneous speed distribution of all the particles, I would like something that's smoothed out in time a bit. So one way we can do that is what we're going to say. We're going to create another variable here. We're going to call it freaks average. This will be the average, an array that will hold lots of different frequencies. And we're going to create the initial value for this. So I'll just go ahead and copy and paste this over. What it's saying is do the initial particle speed histogram with the bins given by this velocity array, and it's going to tile it. So rather than being a single array with all the frequencies for those particular bins, it's going to be a matrix where each row is an array itself. And then we're going to define where we do the frequencies and bins inside each iteration of the loop. What we're going to do is we're going to append, or we're going to change the row in the average matrix. Actually more of a frequency matrix. Let's rename this frequency matrix. What we're going to say is we're going to use the frame variable. So remember, the frame variable counts from 0 to 2399 as each frame is being iterated. So we can use that as a counting variable. And then we're going to use some variable here called n_average, which we'll define in a minute. Then we're going to basically set that row of the matrix to be the frequencies that we've just calculated. So let's do n_average. So plot code, let's have n_average equals 50. So it's going to take 50 frames of the animation, then it's going to calculate the average frequencies of those, and then plot that. So it should be a lot smoother. So for example, a dramatic change during one frame will only represent a 50th of the actual change on the final plot. And then we can get to the mean frequency from this. So we can say the mean frequency, which is just taking this matrix and then doing the average across one of the axes, across the row. So it compresses all the rows together and calculates the average. And then what we're going to plot is going to be from these mean frequencies. Look at that. Sim object has no particle. That where it's particles, actually particle speeds. And that again, and there we go. This now should be a lot smoother because it's basically taking 50 frames worth of data and then showing the average of those 50 frames. And you must admit this is a much nicer plot. It's really showing how the system is evolving over time. I mean, we could do the same as this by adding in a lot more particles. So if we say did 1,000 particles, we'd expect that those small variations to become even less noticeable. Likewise, 1,000,000 particles, it'd become pretty much completely smooth, because even as the particle speeds change, there's so many of them changing at any one time relative, and they represent such a small portion of the overall particles that change should be even less. And now one thing I'm not a fan of is the fact that this plot here remains at 100, even though the distribution goes down. So we start all the particles off at one particular speed, so they all get binned into one particular speed range. But obviously, as they start to collide about and collide off each other, they start to form a distribution. So what we need to do really is to think of a good way to readjust that plot height. So the easiest way would be to, at every single iteration of the loop, and you'll see why this is a bad idea at the minute, what we're going to do is say find the maximum value of the frequency, so over the last, from this average. So we say freaks max, and then we can do it's going to be the maximum value, this variable here, the maximum frequency that's on the bar chart. And then we're going to do, after updating the heights, we're going to do x2 set ylim. We're going to set it from 0 to the maximum height. Yep, run that, and it won't actually do anything. And that's because it is actually doing something, but it's not updating the axes themselves. So this bar here is not 100, so it's not a direct correlation between the two. And that's because we need to tell it to redraw the plot, which is computationally expensive. They start to bounce around of each other. Now we start to see this change. A nice smooth change there. What would actually be quite nice is if you could actually see the top of the bar. So the top of the bar is always the top of the plot. Let's go ahead and add a value to it. Now we can see as the particles start to bounce around off each other, the bottom plot begins to change. Now this has actually slowed our plot down, so if you get an idea of how fast this is going, then I come back here, let's code out, you'll see that it's actually moving a lot faster, and that's because this is an expensive way to draw the plot. So we need to think of a better way of doing this. And I think the easiest way that we can do this, put in something like this, it's basically saying that if the maximum value of our histogram is different to the limit of our axis, or our bottom plot, by more than 10, then we go ahead and rescale the axis by that difference. And this just means that although it's still computationally very slow, and it does make the simulation hiccup every so often when it does change, the actual limits don't change that often, and we'll just go ahead and run that and have a look. So as we see, as this histogram starts to decrease in magnitude, we can see that the limits only change after the height of one of those bars has changed by 10, or should I say the difference between the largest bar and the top of the axis is changed by more than 10. So I think this is very nice because it really shows you some of the nice physics involved. Let's just go down and slow it. So rather than have a time step of 0.5 e to the 2, let's slow it down 40%. Really get an appreciation for what's happening. So all the particles start off with the same speed, and as they start to bounce around off each other, starts to form this lovely distribution, which is given by the Maxwell-Boltzmann equation. And there's nothing fancy here. It's a simple, put some spheres in a box, let them bounce around off each other, let them bounce around off the wall. What happens to the speed distribution? It's very, very nice. It's really building that understanding of physics, like what's actually happening. If I had all these particles with a particular speed, how do they start to distribute? So I think it's really, really nice to do this. And I think that's a good place to leave this video. In the next video, what we'll do is we'll look at the particles in the box and we'll calculate its temperature just to see whether or not the temperature is changing as the particles are bouncing around. Spoiler, they don't. We'll also look how this distribution fits with the theory, so the Maxwell-Boltzmann theory behind it. And then I think it'd be really nice just to see that those physics, and then we can even do something fancy like give a single particle a lot of energy and then see how that evolves in time, see how all the particles then respond to one particle being very energetic. So stay tuned.